Good evening, everyone, and welcome to our February Institute of Physics lecture hosted at the Open University. Well, not at the Open University, but by the Open University. For those who don't know me, my name is Ben Drew. I'm a researcher at the Open University, and I'll be hosting the talk this evening. Tonight, our format is a little bit different due to the importance of our guest and the importance of their talk and work to the Open University. So I hope you'll indulge us a little bit in a bit more exposition than we usually have for these talks. Due to the ongoing pandemic, we're currently continuing to run these talks online for the foreseeable future. I feel that the world has been teasing us with a bit of light at the end of the tunnel, but maybe with some recent developments, it's a bit further off than we all thought. In any case, I do sincerely hope that you're all well at this time. So tonight, there'll be a few more people contributing than usual, as you'll see on the stream tonight, other than myself and the speaker. Among them, we have Sally Jordan, our head of school, who has agreed to give Nick's introduction tonight, and she'll do it a lot more justice than I possibly could. And also we have our Deputy Vice Chancellor of the Open University, Josie Fraser, on the call tonight, who has agreed to give closing remarks to tonight's talk. In terms of IOP business, upcoming talks, at the moment we're still trying to nail down our upcoming talk agenda, but I feel like we're very close to the next few. So please keep an eye out on our Twitter and our website and on the mailing list if you're subscribed. And I'll give you details of how to join that in just a few minutes if you're not already on. And the upcoming talks will be announced there. Now, if you are joining us, let me just share my screen. If you're joining us on the Stadium page tonight, you'll note, and you're a regular, you'll notice there are a few other elements at the bottom here than we normally have. So first of all, if you have any questions to ask Nick during his lecture tonight, please use this link to send an email to this email address, and we will monitor that mailbox for any questions to give to Nick as the lecture goes on. As a little special treat, since Nick is going to be talking a lot about the Open Science Laboratory that he's worked very hard on, we've got a link here to what we call the Open Science Lab Showcase. Now, on here, we've put up, so once you click on that link, you'll come to this page and you'll need to sign up for a free account. And that will give you access to this page. And at the bottom here, there's some information that please read. At the bottom here, there are a number of experiments, and these are experiments that our undergraduate physics students would do in the course of their studies. Some of them are quite interesting, and I think Nick's going to cover a few of them in his talk. So that link will be available for the duration of the talk and for the next week or so. So please come back at your leisure and feel free to explore those experiments and get a taste of how we do our undergraduate laboratory teaching at a distance at the Open University. There's also a YouTube playlist with a number of talks, and Sally's going to just touch on what's in that playlist in her introduction. And also, if you do have time, please consider clicking this link for our demographic Google form. It's a very short questionnaire just with a few demographic questions, and they really help us to understand the audience that we're reaching, and help us to target the broader community so that we get a diverse range of people attending these meetings. Even if you've filled it out at a previous lecture, please fill it out again so we can monitor the evolution of our audience over time. And finally, in order to, if you want to join up, if you want to sign up for marketing emails, please email this email address at the bottom, STEM SPS admin, and ask to be added to the Institute of Physics lectures at the Open University. And someone there will make sure you're on the mailing list and you get future lectures. So I think that's really it from me in terms of IOP introduction. So I want to hand over now to Sally Jordan, our head of school, who's going to give a nice introduction to our speaker tonight.
Thank you very much, Ben. As Ben said, my name is Sally Jordan, and I'm head of the Open University School of Physical Sciences and Professor of Physics Education. It's my privilege and honour, I think I'd say, to introduce tonight's speaker, Professor Nick Braithwaite. I'm actually going to spend a few minutes setting this evening's event in a wider context as well, and I think I'm fair in speaking for everybody to say that it's a context that I and the colleagues you can see with me on the screen are all very, very proud of. Towards the end of last year, Nick was awarded the Institute of Physics Lawrence Bragg Medal and Prize. I'm going to call it the Bragg Medal. The Bragg Medal's awarded for physics education. It's a significant achievement, recognised by the fact that the Bragg Medal is one of the Institute of Physics gold medals, of which just 6 are awarded each year. The brief citation to Nick's award is that it's for his outstanding contributions to the authentic teaching of practical science through the development of the award-winning OpenSTEM Labs, available to learners in all places and at all times. I'm going to unpick some of those words a bit more. I suspect Nick will do so as well. Nick's currently the Executive Dean of the Open University's Faculty of Science, Technology, Engineering and Maths, STEM. He's also Professor of Engineering Physics. He's spent much of his career researching plasma physics, and I suspect we'll come back to some plasmas later on, though he's now also got substantial interests in STEM educational research and has contributed to the Open University curriculum across all levels. Nick's unusual in that he's worked across more than one department at the Open University, and in fact more than one faculty as well, and that's not just because of faculty changes in structure. But his academic home is now in the School of Physical Sciences with us. Nick isn't the first person at the Open University to be awarded the Bragg Medal. In 2000, it was awarded to Professor Russell Stannard. Then in 2002, it was awarded jointly to Professor Robert Lambourne, along with the late Mike Tinker, who was at the University of Reading, but he was also a long-standing Open University Associate Lecturer. I hope that Bob Lambourne is watching tonight, and I would very strongly recommend the recording of the lecture that Russ Stannard gave to us back in January 2020, which is on that playlist that Ben alluded to. And there are many other talks there from others I'm about to mention. As well as being Bragg Medal winners, Russ, Bob and Nick share the common distinction, you might say that, of having also been head of what was the Open University's Department of Physics, which under the leadership of the late Professor Barry Jones became the Department of Physics and Astronomy. Professor Dame Jocelyn Bell-Burnell, who I'm sure needs absolutely no introduction from me, is another one of our former heads of department. And amongst many well-deserved accolades, Jocelyn was awarded the Institute of Physics President's Medal in 2017, and just earlier this year she received the Royal Astronomical Society's Gold Medal. Following various mergers, we became part of the Department of Physical Sciences, and Professor Monica Grady, who's with us tonight, was founding head of department. I took over from Monica. I feel humbled to be guardian of such a prestigious heritage. Before screen sharing for a minute, I just want to introduce you to the two others, other than Josie, who you'll hear from later, who are on the screen with us. So the first of the people is Dr. Alan Kalis, who's a long-standing role in the development of the teaching of practical physics and astronomy at the Open University, and he's currently chair of our module Remote Experiments in Physics and Space, which makes use of a number of the OpenSTEM Labs experiments that Nick will be describing later. And last but by no means least, Dr. Ulrich Kolb is our Director of Teaching and also Director of the Open Science Observatories. And he's made absolutely huge contributions to the remote teaching of practical astronomy. Now there comes the inelegant bit where I share my screen with you. So I'd like to highlight the ways, just for the final couple of minutes that I'm speaking, the ways in which since the Open University's foundation, we've led the world in our teaching of practical physics to remote learners. So if you look at the screen in front of you, on the left-hand side, there's a picture taken at one of our residential schools. They were fantastic. We still run some of them. But of course, not everybody can get away to get to residential school. Moving on to the picture in the middle, that's me sitting looking at one of our rather large experimental kits. They were great as well. And in fact, we also, moving on to the right-hand photograph, we've always run home experiments making use of everyday items. So, for example, one of the experiments I used to do a lot, you took one broom handle, one coin, and using those, you were able to measure the distance to the moon. But returning to the screen, on that, we supplied students with a diffraction grating. That's the thing that you've got the coloured images on. Everything else on that photograph were objects around my house. There's a shoebox, there's some blue tack, there's a pin, it's a piece of cotton. Using those things, I was able to actually take really accurate measurements about the wavelength of light. It worked really well. I actually did that experiment on the table that I'm speaking to you from tonight, but it was fine for me. I was down on my knees taking the measurement, but it did need a certain dexterity and a certain visual acuity as well. So we moved on to using interactive screen experiments, ISEs. And the bottom left screen has an ISE version of a residential school spectrometer activity, but students were actually able to do it from their own computer screen. The significant thing, which I know that Nick will be picking up on, is that it's not a simulation. It's based on photographs of the real experiment in action. And just to prove the point, the photograph on the bottom right is a photograph of the filming of the ISE based on the home experiment that's top right. So in addition to giving access to those who would be otherwise precluded from the experiment, we were trying to give authenticity. At which point, before stealing any more of his thunder, it gives me great pleasure to hand over to Professor Nick Braithwaite, Executive Dean of our STEM faculty and 2020 winner of the Institute of Physics Lawrence Bragg Medal and Prize, who's going to talk about X-rays, waves and particles, seeing from a distance. Now I have to get out of this.
Sorry, Nick, you're muted.
Nick.
That's because I did as I was told earlier and muted my microphone. Good evening. What I was just saying was, Sally, thank you very much for that fine introduction, putting everything in context. And it's a pleasure to be here giving this lecture this evening. And it is an absolute honour to be the recipient of this particular medal, the Bragg Medal. The more I have discovered about it, the more honoured I have become about Bragg and the work that he was doing. So I'm picking up on some of that this evening. That's why we're going to talk about X-rays. Waves and particles are something we investigate in some of our online practical experiments that Alan Kalis is overseeing the presentation of. And seeing from a distance, well, there's a bit of a pun in that because you do see from a distance with X-rays, and also the way that our students enter the lab is from a distance so that they can see from a distance. But it's to do with doing, and it's to do with discovery learning. Let's get going. You can't go any further without starting the slideshow, and then we need to go to the first bit. If you're going to talk about X-rays, you have to mention William Conrad Röntgen. He got a Nobel Prize for his work in 1981. It wasn't just a Nobel Prize in physics, it was the first Nobel Prize in physics. And there's a nice little bit at the bottom of this slide that indicates that in actual fact, he was unfairly dismissed expelled from school for having produced a caricature of one of the teachers. And in fact, it turned out it is said to have been done by somebody else. Whether or not he did it, I don't know, but I could have been there doing exactly that. What a fine spirit of a person. Let's move on and look at a piece of equipment. This is of the form used by him. It's from the Science Museum. It is a large pear-shaped tube of the form originally used by Röntgen, manufactured in Germany about 1896. Now, he did his pioneering work with X-rays in 1895. So if this one was manufactured in 1896, he couldn't possibly have used it, but he must have had one pretty similar. So I want to have a look a little bit about what it was doing. He'd had an electrode at one end inside this glass cylinder. This is a 10 centimetre range I've put on the slide at the bottom. It's about 4 inches in old money. And there's a positive electrode at this end, and you put a high voltage between these two. The gas has been removed from the tube. Mostly, there's still a little bit of gas there. So what on earth is going on with that? I think I want to find that out by going to my laboratory in Milton Keynes. Right now, I'm not there. I'm 35 miles away, about 50 kilometers, I suppose, in those units. What you're looking at here is a picture of an experimental apparatus. It's a vacuum vessel. There's a ruler down here, a 30 centimeter ruler. So that gives you an idea. This is, again, about 10 centimeters across there. I'm going to turn it on before I go any further because it has to pump down. And I've just got a little bit of residual noise in the background. I can hear that the pump has turned on. In a minute, you'll be able to see that because the pressure gauge here will start to fall. And, I'd also got 600 volts between 2 electrodes. You can't quite see them in there. You can see something limiting. In the little diagram here, you can see there are 2 plates facing each other. That's what it's trying to show. And there is a gas conducting electricity in the space in between. And it's just gone out. So what I'm going to do is to stop the pump and let it come back on again. And we will zoom in on the camera as well so we can get a bit closer and see it. This is the same kind of experiment that Röntgen was doing. And he was doing it at slightly lower pressure. But I just put it on again there. And you see this, it's glowing in a region. There's negative electrode on the right, positive electrode on the left. Again, I'm going to just turn it off and let the pressure just creep up a little bit. I was playing with this afternoon just to make sure that everything was all right. And I found that we'd run out of gas. So I asked somebody to go in and just put the gas bottle on for me. But I think it's run out again. I'll put it back on again one more time just to light it up, just to show that there it is. And what's happening as the pressure falls is that part of the discharge moves over to the left. But the way this thing is working is that the positive particles are bombarding the electrode on the right. That's producing negative particles, electrons being released from that surface. They're being accelerated across and hitting the positive side. They do it, and they hit it with enough energy to just begin to produce X-rays. Not very strong X-rays. We don't need to get the X-ray badges out for this one because they won't even get through the glass at this energy. But what Röntgen was doing, and we'll go back to him now, we can leave that experiment turned off. And here we are. What Röntgen was doing was working at lower pressure and putting more volts across here. And his negative particles were coming down here. And with the use of the judicious use of magnets, he was able to steer the beam onto the end face. I've just zoomed in and showing you a little bit more of the end face here. This is the end of that tube. And you can just see, I hope, some damage to the tube. It's damage on the inside of the tube where that beam of negative particles has been slamming into it. And it's that impact which gave rise to some X-rays. What he found was that if he, now putting in the electric circuit, just schematically, there's a little meter here to measure some current, batteries indicating some large voltage, and I'm talking about a few kilovolts, and a switch, of course, and then we close the switch and see what happens. And what happened was that a little plate that he had over here, he happened to have a plate of fluorescent material. He was a tinkerer like me, and you've often got bits like that in the drawer hanging on the wall. And when he opened the switch, it didn't fluoresce at all. And when he closed the switch, it did. Now, what do you do then if you're somebody like Röntgen, 1895? It was actually in November 1895, so it's just 125 years ago. He says, here's a strange thing. Whenever there's a current in that tube, then that fluorescent plate some feet away, is lighting up. That's a little bit strange. And I've called this thinking outside the box, because what he then did was he put his tube in a box, covered it over, and he did the experiment with the tube in a box, and it was exactly the same. This thing lit up when there was current flowing in that tube. Breakdown of the gas was somehow giving rise to something which went across. And so what I've got here is the continuation of it. What he was saying is, okay, I mean, I wasn't there, and he would be speaking German, so I'm just paraphrasing what it must have been like, I'm sure. Let's call the things that pass from the tube to the fluorescent plate X-rays. X because it's unknown. Well, that's what he says in, if you look it up in Wikipedia, if you look it up in textbooks and so on. I don't actually know whether he said that. It's not a bad idea to call something you don't know X, but there are so many things we don't know, we can't always call them X. I don't know why it's stuck with X-rays, actually. Anyway, by 1905, things were moving. And actually, this is a 1905, or maybe even in 1896, I've revised that date, actually. This chap, Crookes, who was designing tubes just like that one that we just saw for experimenters to begin, actually, the subject of plasma physics. He saw what was happening with Röntgen and decided that there was a slightly better way to do it. Instead of slamming those negative particles into the end, slam them into a piece of metal, put a piece of metal in there, insert it there, make that the positive thing, get some of this negative charge up the tube, banging into that, and then X-rays would come out in this direction. So that was what Crookes decided to do. And by 1896, he was designing tubes by that. I know that, although that date on there is from the Wikipedia source, which dated it at 1905, I happen to know that this was being designed in 1896 to 97 by a very young chap, Russell John Reynolds, said to be only 15 years old at the time. I don't know, I wasn't there, I haven't seen his birth certificate, but that's what the report is. This he designed with somebody else. He joined somebody quite a bit older with a lot more experience. This is a coil that's used to make the high voltage. And here is the tube. This is just the same tube that I was showing in the previous picture. This time it's marked horizontally. And this generates X-rays. And we'll come to the sorts of things you can do with that in just a moment. You see, Röntgen himself was playing with something very similar. And by 1906, his own equipment had developed. And look, he's got one of these tubes as well. He's gone out and bought one of the Crookes tubes to make his X-rays. Here's his coil, looks a bit like the kit. And here's the sense of scale, about 10 centimeters there. He's making his X-rays in here, and they're going to go in this direction, and he's going to detect them in this bit. It's worth seeing how he detects them, so let's draw that in. X-ray source, a zone of interaction for doing some things maybe there, and this piece of board is possibly in that interaction zone, and then a detector. How do you detect X-rays? Nowadays you can buy little channel plates, little camera plates almost, that will detect X-rays. In those days they didn't have that technology. They had to think from the basics, and the one thing that they knew, they knew two things. They knew that it caused fluorescence on the plate, and they also knew that it would cause charged particles to be created from just in the air. It would ionize the air, make positive and negative charges in the air. And these plates here and here, marked over here in the little line drawing, is the X-rays coming across. Positive and negative charges caused by the energetic, whatever it is, X-rays, streaming across into that zone, actually making probably positive and negative charges in other places too, but we'll just look at these here. And a small voltage applied between these two plates, and a gold leaf electroscope, which is just a pair of gold leaves coming down, and then the leaves will splay apart when charge accumulates on the plate, is a measure of how much is happening, how much X-rays are entering this ionization space here. Absolutely beautiful, very simple experimental work. But look, a source, an interaction zone, and a detector. With that, you can begin to do some very interesting stuff. Time went on, and somebody called Coolidge, who'd been making light bulbs in the United States, he got hold of this and he said, oh, wait a minute, I can make better X-rays than that. What you need, instead of having to get X-rays out of a metal plate, by hammering positive charge into it, why don't you just make a very hot filament, a little glowing bit like we have in our incandescent bulbs now, and that will boil off some negative charge, and you can then accelerate that with your voltage. It'll be more efficient. And so this is the Coolidge version of the tube. Now, in the OpenSTEM Labs, we've got something that actually emulates that, so I'm going to take you to it. I've just loaded it up. The software is now downloading onto my computer, and in a moment it will be ready. What you're seeing is a bit hard to see, I know, but I'll tell you about what it is. There's a glass sphere, which is about that size. And it's got some electrical connections in from the left and the right. And there's a little bit glowing here, and it'll become a little clearer in a moment. And then there are two rings around the outside, which are magnetic coils. They produce a magnetic field which goes into the screen or comes out of the screen, but it doesn't go sideways. That little glowing filament, if I apply some volts to a plate very near it, I can pull some of the negative charges, the electrons, I can pull them off, accelerate them, and give them a voltage. And here's the control for this. And there's a hole in that plate. So the ones that actually come where the hole is go straight through the hole. And that's this lot down here. Now, electrons aren't blue. You're not seeing electrons. You're seeing where electrons have been, because there's a little bit of residual gas in this sphere, the sphere around here, and they're exciting that gas, and they're causing it to glow a little bit. So that's mapping out the trail of the electrons. Now, if I put a magnetic field into the screen or out of the screen, and I use rules of how charge flows interact with magnetic fields, I should be able to make that thing curl in a curved path. And I'm increasing the current in the coils. That's an electromagnet, making the field stronger. And eventually I can go round in a circle. Now, this is a real experiment. What we've done is we've recorded every combination of voltage on this side and current on this side, taken a photograph, and I'm replaying this experiment. It was done about 15 years ago, and I'm replaying it now for you on demand. And I could make some measurements, and they would be accurate measurements of what goes on in a tube like this. I could use this instrument here to measure the diameter of that. I could check that it's circular. I might have some screen distortion, but that would distort my ruler as well, so that'll be fine. I can make measurements on this, and it's a real experiment. It's what we call the interactive screen experiment. There isn't a piece of equipment doing this in Milton Keynes at the moment. There could be. We've done the experiment. We've thought about doing this experiment that way, but this works very well. It's very deterministic, just two knobs to control, but it allows you, on this occasion, to determine the charge to mass ratio of the electron, which is a very fundamental thing and very exciting for physicists to have a go at. I can remember when I was at school, people got me to move a ruler, to get a ruler acting as a pendulum so that we could measure the acceleration due to gravity. And I was really upset. I couldn't understand why they were asking me to measure it, because there were much better experimental scientists around who'd already measured it far more accurately than ever I could. I didn't realize actually what they were trying to do is to just show me the importance of just trying things for yourself, just getting that feel of getting hold of it and asking what if the ruler were twice as long, what if I break the ruler in half, and just being in that space and being able to do it is really important. So I think what we're doing with our experiments is giving people that ability to learn in context. Meanwhile, by 2010, then we get to a tube here. This is the modern version of the Coolidge tube. There is a hot filament in there. This is the anode material, and we can shoot electrons across, accelerate them into there with several kilovolts, really get them moving, and they produce X-rays. There's a little go to the OpenSTEM Labs again here, so we better do as we're told and go there. Now, this is in Milton Keynes, and it is there now, and this is going to be a live experiment, and we're going to do it. This is our X-ray apparatus. Until yesterday, it was being used by our students. Last night, 3 pairs of students were using this up until about 11:30 at night. The last pair went through, getting their results. So what are you seeing? This is the Coolidge tube here. And the scale on here, that's again about my 10 centimeter kind of scale across there, that window. This is going to produce some X-rays. Over here, there is a detector, which is going to see. But I want to do an initial experiment. I want to set things up a little bit. I want to show that I can control this. So I'm going to move the detector, and I'm going to move it around to, I don't know, about here, somewhere like that. And I'm going to move this around. This is a target. I'll show you. If you watch the image in a moment, you'll see what's moving. Well, I want to stop that at about 20. It doesn't matter greatly. And when we do an experiment, we'll do it for about 240 seconds, I think, and then talk some more while this is happening. Ooh, 240. Okay, and we say that should work. And now you see this is the detector being moved around that angle. It's doing it in real time now. This is a live photograph that I'm seeing. Because if you're watching a recording of this presentation, then it was happening while the lecture was live rather than actually happening here. And then there's a little target in here, which is a piece of perspex on this occasion, and it's just been aligned at a slight grazing angle. And I can start the tube. It's going to check that the door's closed. It's going to say that it's safe. And when it is, it says it's okay. Now the tube lights up. So there's about a little hot electron source, slamming electrons into a cathode. They're then coming sideways, and they're hitting this target here, and they're being scattered up into the detector. And in real time, over here, you can see some signal. I'll call it signal for now. Let's work out what it is. This scale here, it says channel. These are energy channels. So it's an energy scale. It's a range of energies across this region here. Higher energies at this end, there seems to be a maximum energy, and that's associated with this 30 kilovolts that I put on the tube. And down here, it must go towards zero somewhere, but I can't get zero energy X-rays. They've got to have a certain energy before they're called X-rays, or whatever they are. But you just see this coming up now. It's forming a peak, and it's also got some kind of background to it. That's a really nice, interesting thing, and we'll come back to the nature of that in just a moment. For now, I want you to note something, and it's going to depend on how clear the screen is, or if I roll over, I can see where this peak is. And you see, it just picks off that data there. It says, look, that highest peak there it's about 256, 258. No, it's to the left. There we are, 255. It looks as if channel number 255 corresponds to the energy of the peak of that. I want you to remember 255. We're going to come back later and carry on with that experiment. It's going to go on for a little bit longer. It's 90 seconds. It'll go on for 240 seconds. But I don't think it's going to change its mind about where the peak is, around about 255. So I'll leave that just finishing off, and I'll come back to the PowerPoint. So let's talk about Bragg. There are two Braggs here, buy one, get one free. We've got William Bragg on the left and so-called Lawrence Bragg, professionally, on the right. Actually, he was called Willie when he was at home. And William Bragg Sr., his father, born in the UK, went out to Australia to a university job in Adelaide. Young Willie was born there. So he was born in Australia, and what happens in the next slide is I think he probably falls off his tricycle, but we'll come to that. So these are clearly not shown at the stage when he was riding tricycles and falling off. I think it's about 20 years after that incident. But here it is. In 1896, W.L. Bragg, Lawrence Bragg, fell off his tricycle and he severely injured his arm. And I imagine his dad said something like this: give me an hour or so and I can look at that. He says, Dad, as a physicist, engineer, mathematician, he'd started off doing mathematics. And he'd heard about these X-ray things. And he had a few things, I suppose, in the shed. And he possibly had even seen what this apparatus was that I've got here from the Science Museum. And he decided to manufacture one. Now, he couldn't have manufactured this tube very easily. He must have had one of these anyway and been doing some experiments on something like this. You'd need more than an hour to make one of those. Anyway, so I suspect he probably just said, just lie down there, rest that poorly arm next to this camera plate, sealed in a light-tight box at the bottom here, and keep still while I connect the high voltage and produce X-rays. And they produce an image, just like they were lighting up the fluorescent screen inside a box. They can go through into a light-tight box and expose a photographic plate, creating a shadow image of young Bragg's broken elbow, broken arm. Now, the story is then told by Bragg himself that it was suggested that by one doctor that they should just set the arm in a convenient position. I'm not sure whether that would be straight or slightly bent. But his father decided that he'd get a second opinion, and they decided not to set it in a fixed position, but to set it for a day and then make sure it was still moving, and then set it and keep moving it. And he got reasonable use out of it, I'm glad to say. I must say, doing an experiment like that, very dangerous, really, now that we know what we know about X-rays, a little unguarded. But such is the nature of discovery experiment. I'm sure they were thinking as safely as they could, but what we know now is a bit different. How many times have we heard that kind of story about things? Certainly about X-rays, certainly about things like asbestos. We learn, and we should proceed carefully and cautiously. So carefully and cautiously that for a long time, when the dentist said, "Oh, I'll just take an X-ray," I said, "Can't you manage without?" But X-ray technology has come on a long way. These are my teeth taken just a couple of months ago. You can see the root canal work that's been done here. And this is a bit of a clip. This white region here is a bit of a clip, but that's clearly recognizably a tooth. They're not the greatest of images, but they were done with very low dose nowadays. And it wasn't done with film. It's done, if you've had this done, they put a little detector plate, little camera plate essentially in your mouth, inside a polythene bag. And the image comes up within just a few moments. And there's another picture of other teeth of mine there. You can see I've invested a great deal in this dental practice over the years. Well, meanwhile, back in 1895 to 1915, 20 really exciting years to be in physics. Actually, they're probably all exciting years, but these are exciting for today. There were various university-based researchers and clinicians across the Western world, across Europe, certainly US, Australia, may have been happening in other parts too, but not known to me. There was a lot of uncertainty as to what X-rays were. Some said they were waves. Some said they were sort of bundles of waves, and others said particles. So experiments suggested that there seemed to be at least two contributions to the X-rays. And this is Röntgen's kit, as we saw in 1906, and he was one of the European groups still plugging away. I'm being told to go back to the lab, so let's just go back to the lab again and see where we are. Oh, that's the end of the experiment. It did its 240 seconds look, and it's decided the peak was at 255. Did you remember that? And do remember it some more, because we'll change the settings later on and can come back to that particular experiment. But that was an X-ray experiment operated this time at a very safe distance. But there seem to be two things about this. There is no doubt some peak structure, and peak structure on things like that excite physicists no end, because it says there's something very definite about that. We ought to be able to do some theory, some thinking, some modeling that says why exactly at that point. And then there's a sort of background, a broader structure here. And in actual fact, it turns out, and they were beginning to tumble to this, that there are two contributions to these X-rays. And remember, this range is energy. So we've got a range of energies. This is the amount of stuff that I've got at that energy. And at this particular energy, there's a very specific energy. There's a lot of stuff. That turns out to be to do with the metal that you're slamming the negative charge into. And then there's this general background, which is emitted by those negative charges as they slow down. They come out of the gas phase and they bang into the solid, and they, in a very short space, they have to slow down and lose their energy. And when they do that, they emit, it's called braking radiation. Well, Röntgen was there first, and I suspect it was probably him or his colleagues who called it Bremsstrahlung, which is, I think Ulrich would tell me, it means that the same thing. It's from the braking, from the slowing down, the rapid deceleration of this negative charge. And then what it hits gives you a particular feature here. Well, what about these features here? What, is it hitting something else? And the answer is yes, these two features here actually are to do with some gold, which is around the detector, just near the detector, and it fluoresces. It glows like that plate did in Röntgen's lab all those years ago. And here it is happening in our lab now. Right, so 1895 to 1915, what's going on then? They're talking about radioactivity, alpha, beta, gamma. They weren't sure of things to call. They could have gone further down the Greek alphabet, I suppose. But they were still X-rays. The name stuck. WHB, that's Bragg Senior, he preferred the view that X-rays were neutral particles. his reasoning was a little bit like the reasoning that Einstein was using at the same time to explain the photoelectric effect, ultraviolet light on metals. And it was really to do with the way that his ionization detector worked. It didn't matter how far away he put it, it still seemed to work in the same way. And that rather suggests that these things weren't losing energy just by distance. There was something very special about the energy that they had. But he wanted to claim that it was electrically neutral by having an equal and opposite pair of charges. At this stage, the electron was not properly understood, or not properly described, and the positron, a positively charged electron, was utterly inconceivable. That was going to come 20 years or so later. So we were well off the pace for knowing what it was. It was just hypothesizing. And that's what you do. You say, what if there were two charges next to each other, somehow being persuaded not to recombine, then they wouldn't be deflected by a magnetic field because the charges cancel each other out in some way. That was his thinking. Whereas younger Bragg, by this time they'd come back to the UK. Bragg Senior was in Leeds, and he did a lot of work in Leeds on X-rays. Bragg Junior had gone to Cambridge to study. I think there was a university there. That was the reason why. And he went home in the vacations to go and do experiments in his dad's lab. And he was saying, look, what they're finding in the other places, because they talked, lots of communication. Lowy in Zurich, in particular, they're finding things that make it look like these things could be diffracted by crystals. And in fact, in 1914, Max von Laue picked up another Nobel Prize in physics for exactly that phenomenon. They were shining X-rays on crystals and getting very precise patterns of dots of bright light on a photographic plate at some distance away. And it was characteristic of some diffraction phenomena that should happen. Lots more international work going on. And then a year after that Nobel Prize, it was a couple of years before that Nobel Prize, around about 1912, I think. William Bragg was putting together the different findings and thinking and so on. So this is the only maths in the lecture, but just bear with me. We're now going to think the kind of thoughts that I think Lawrence Bragg was having when he was thinking about what happens when you shine these X-rays, thinking they're going to be diffracted, shining them like waves onto crystals, which have got planes of atoms in them. That's the way that people were thinking at the time. So I've indicated here a couple of planes of atoms. In the end, we're just going to concentrate on these two. But this is a wave. This is trying to show a wave, the peaks and troughs of a wave riding in towards these two atoms. Let's see what happens now. Well, those two atoms, they get excited by the wave, and in some way they get caused to re-radiate it. That does happen, and that's the way that light propagates through media, that the electrons in the media get excited up and down, and they re-radiate the energy. So these two atomic sources now re-radiate. So what's so special about that? What's special is because they re-radiate in all directions, but they were only excited from one direction. They were excited by the radiation coming in, and then they re-radiate on the way out. But it turns out, and I've just set this picture up so that it is, that these overlap, these peaks overlap, if you just get the condition right. And the condition is that as the light coming in, the one that gets here has a quick journey, and the one that has to come this way has to go this bit further, that bit further, and then the rest of the journey. So this peak here is one distance behind that one wavelength, the distance between two crests. So that was Bragg's proposition. He said, look, if this were the case, wherever you get this combination of wavelength, the distance between the crests, this angle theta at which is coming in, and this distance d between two planes of atoms that are doing the scattering, then you should get constructive interference in that direction and only in that direction. Everywhere else it will all randomize out, cancel each other out. And then he said, actually, it doesn't have to be one wavelength. If it were two wavelengths or three, so long as it's a whole number of wavelengths, then you would get in this direction constructive interference. That would be a diffraction phenomenon. We ought to be able to see that. Why don't we look for it? And it became, ever since then, people were kind enough to say, let's call it Bragg's law. Actually, he's always written Bragg's law with the apostrophe here, but because there are two Braggs involved, maybe the apostrophe should be further down. Here is that same experimental apparatus that we have in the lab, but this is a photograph of it, set up to do a Bragg experiment. You can see the filaments on. This is a Coolidge tube. We're accelerating the charge across there. We're producing X-rays which come down here. The slide was just showing that I've got a source. I've got a detector. Here's the interaction region. This time the target is salt. It's a crystal, a single crystal of salt, and it's going to come in a special way. And it turns out that to do this experiment, you need the angle between the incoming beam and the sloping crystal, and the angle between the sloping crystal and the detector, both to be the same thing. So, and you have to you rotate the crystal and you rotate the detector on top of the crystal. And if you do that, you find that at some angles of rotation, you get a very strong signal through. And then there's another one here, and then there's another one here. But at other angles, you hardly get anything. So it's as if it flashes at particular angles. It just becomes very reflective. Well, it's not reflection, it's diffraction. And this is Bragg diffraction. This is Bragg's law. And what you're seeing here is n equals 1, 2, and 3. 1, 2, and 3. So the subject of crystallography is born. And it's down to the Braggs. They made a career of it. And from 1915 to 1916, Lawrence Bragg, working mainly in Leeds, that time, did an awful lot of work developing this whole new subject. In fact, it leads to molecular biology and terrific insights. There's a great story about it told by Melvyn Bragg, who is a distant relation of these Braggs, and it's on BBC Sounds. It's 25 minutes. I can recommend it to you. It's a thoroughly good story. It tells it very well. So there we are. They're waves. X-rays are waves. Job done. No. Unfortunately, in 1920s, along comes Compton, who says, wait a minute, doing some more experiments. We found now that if we bring a wave of X-rays in here, a beam of X-rays, and if they scatter off something, that is, if they hit something and then get moved off at some angle, maybe they're scattering off an electron. Where are electrons? So that's a little bit of charge. Matter is full of them. So just put a little bit of, I don't know, a little bit of perspex or something like that, a little bit of plastic, lots of electrons, and that could be a metal, doesn't matter. Actually, the experiment we do, we use a little bit of plastic. In comes the X-ray, out goes the X-ray. Electron gets scattered, quite high energy and hard to get, but we can pick up this X-ray, same as we can pick up this incoming X-ray. So that's what he was doing. And he said, well, these X-rays have got energy and momentum. Let's say if they're a particle that have energy and momentum, if they're a wave, I don't know. But let's play. Well, by this time we can play special relativity because these things are going fast. They're going at the speed of light, possibly. And we're trying to say, in the way that we're diffracting, that they are waves related to light. So we better do some relativistic mechanics. I'm not going to do it. Don't worry. But if what you find from this is that not only does the scattered X-ray lose energy, so it's coming out with slightly less energy because it's given some to the electron, but it also, the relationship, the angular relationship and the energy relationship are tied together. And you ought to be able to do an experiment. And he was right. A Nobel Prize came his way in 1927 for getting that right and saying, thank you. Here's the question then. Are they particles or waves? And here's the answer. Yes, they're both. Let's go back to the OpenSTEM Labs, to our experiment here. And you remember where we got a peak before? It was at channel 225, you remember that? Let's change the settings. Let's now move it around. I'm going to move this back to 0. So this now is, the detector is going to look straight at the X-rays. So we won't do it for very long. Won't need to do it for very long. We're going straight in. I'm going to rotate the target to minus 90. You'll see why in a minute. And I think we'll just do this for about 30 seconds. So just again, it's a real experiment. We're going to do it together. Your part in this is to remember where the peak was before. We're going to see where the peak is now. So we'll say OK to that. The apparatus will reset. There's a little diagram here that shows what's happening as well. And now the X-rays are going to come down this hole here from the Coolidge Tube, and they're going to come to our target, and we've drilled a hole in the target at exactly this position. So it won't see the target, there won't be any scattering, it goes straight through into the detector. So this is just the straight through looking at the neat X-rays. And we ask it to start, and it says, OK, the tube lights up, the X-rays come through, there should be something. Remember, this is energy along here, this is number of counts. I've got a peak, I'm a physicist, I'm excited. And it's coming up here. I wonder where it's coming up. We'll probe it in a minute. All these other peaks that were there before, they look as if they're still kind of here. There's a background. Remember that Bremsstrahlung background? And this peak is characteristic of the metals that are inside this Coolidge tube. So that's all adding up. Let's see where this peak is going. 28, 29 seconds. There's the peak now. And the peak is at channel 269. This is at higher energy. 255 is where it was when we were around at that big angle of scattering, and now it's not scattering at all, it's going straight through. So this is the raw X-ray, and it's a peak of 269. We haven't calibrated this scale. We'd have to calibrate it. Physics is full of calibrations. It's full of getting rid of the noise. We need more data. But this is what our students can learn. They can go back now and say, I need to do this run again. I need to run it for longer. I need to... I need possibly to order a different experiment. I mean, at the moment we're giving them the X-ray tube, and none has come back and asked for a different X-ray tube yet. But I guess if some did, I'd be prepared to. We've got a few spares, a few different ones. I'd be prepared to respond to that what-if kind of question. That's what we do for our students, working at a distance, exploring practical science at a distance. So what we've done is Compton's experiment now. Compton got a Nobel Prize for it. Nothing for it doing it tonight, I'm afraid. Well, the story goes on to more recent times. 1962, another Nobel Prize kicking around for Crick, Watson, and Wilkins on the structure of DNA. And it's unfortunate. The contribution of Rosalind Franklin was overlooked. She was working well, she moved universities in the middle of this, but she'd been doing some X-ray crystallography. And she took this particular X-ray photograph here, these shaded bits of where X-rays have developed to expose the plate. And this white circle in the middle is where it was so intense. I think they blocked it out altogether. But this is a key picture, and it was used, it's almost certainly used by Crick and Watson in their deliberations about what the structure of DNA was. She was working on big protein molecules. She also, unfortunately, by the time the prize was awarded, she had died a couple of years earlier. That shouldn't have been an excuse, and the recognition should have come her way. But you know, Sally was mentioning Jocelyn Bell Burnell, who found herself in a similar position of just not getting the credit for the work. But she says sometimes that she feels she's done very well out of not getting a Nobel Prize. And I think you could say the same maybe about Rosalind Franklin. There is a rover waiting to set off to Mars. There's a lot arriving in the next few days, but this one is setting off next year. And it's called Rosalind Franklin, which I think is rather nice. It's going to be on Mars. We've got some interest in it. One of my colleagues is looking after the camera that sits on the top here, and there's a whole pack of instruments underneath here. I mean, they give these things names to honour different people, and this was an appropriate honour. It's a pity that it doesn't actually have an X-ray instrument on board. There was going to be an X-ray instrument on board. There was one scoped, but they decided in the end they couldn't take it. There's always competition for what instruments you put on board. But if they had, they would be looking directly at the minerals on the moon, doing that kind of Bragg experiment that we were doing, or looking at the fluorescence, the slight shifting of energy of X-rays when they interact with different materials. So let me just turn now just a few slides about the OpenSTEM Labs and seeing from a distance in the period 71 to 21. Sally's picked up some of this, so I'm just going to resonate with what she was saying. We've had home experiment kits here. She mentioned the kitchen sink, but didn't show us her kitchen sink. This is a kitchen sink, look, and here we've got two very keen students with their home experiment kit, getting it out and doing their practical work at home. I think there are things that we've done in the past that you'd find hard in today's society to get away with. And we've sent lasers to people to have them do experiments on holography at home. Nowadays, you wouldn't do that sort of thing. Certainly, if you've got international students, sending them through the post and so on, it got a lot harder. TV broadcasts and videos. We've done some of that. Here is Patrick Statland. this is, Sally was mentioned that he got the Bragg medal several years ago for the Albert stories, Uncle Albert stories about Einstein, children's stories. And here he is demonstrating something on television. Later on, they became videos. We tried residential schools. Here's a residential school with 2 students. I have checked they are wearing goggles when they're looking inside a fume cupboard to see something happening, being there in the lab. That's students coming to the lab. What we're trying to do with the OpenSTEM Labs is taking the lab to the students. We've flirted with CDs, DVDs, and now we have the OpenSTEM Labs as well. And we'll use any or all of these as appropriate. The OpenSTEM Labs idea is that we have this central facility, we have the internet, and students interacting with equipment, possibly also interacting with each other across the ether as well. No reason why they shouldn't be working in pairs. In fact, in the telescopes that Ulrich has got on Tenerife, they can work in groups of 5 or more. Now, the thing about the OpenSTEM Labs as well is that what we've done from the very start, the whole concept, we knitted it into our curriculum. We've got teaching to do, and we wanted to make sure that we were teaching our students this way rather than just looking at it casually. And so I like to show this one. This is a project iLabs MIT, quite a go-ahead place in the States for teaching physics, with the support of Microsoft. They make some kind of computer, I think. I come across them sometimes. They've got lots of money, and they invested in this between 2006, 2013-ish, and they had remote access experiments, and some of them were freely available. But I don't know that they were quite embedded in the curriculum. I don't think they quite had the need that we had. Necessity is the mother of invention. They didn't have the need. And so in 2019, it says rather sadly on their sites, the project has come to a close. This site's being left there as a historical record. Well, we started in 2013-14, and we're still here. And as long as we're teaching students about STEM subjects, there will have to be some OpenSTEM Lab presence. But, you know, this is built on stuff that goes back in time. These are Open University colleagues in 2002 to 2004. They had a project that was to do with remote access, remote experiments, reversioning, rethinking science learning, looking at the pedagogy of it. And what they had here was one of those summer school experiments. Actually, Sally showed an aerial view of this particular experiment. It's a spectrometer experiment. And what they did was they just tried to replace the person and put cameras and motors and things. It's the way that you would start. It's the way that we thought to start. But after a while, you realize that actually this is new, and you've got to design it to do what you want rather than to just substitute one part with a dummy human being, because it'll never be quite the same as the human being. So you design the experiment in a different way. Anyway, Chet's Colwell, I think she took early retirement recently, but Eileen Scanlon is still very much with us, working on pedagogy, teaching. This is their interface. It's not looking that old, given the fact that it is 15 years old. Here are some camera shots close up on a scale, and then a wide shot on the instrument, and then looking down a particular telescope tube, which you do. But as I say, I think if you were to do this now, if we were to do this very experiment now, we wouldn't quite do it that way. Here's Sally's experiment. This is a diffraction grating. This is the thing that she was talking about. Actually, in the next shot, I put the person's head in here. If you're doing the real experiment, you have your head here and you move it from side to side, holding a pin here and trying to align it with a color on this 35mm slide, which is part of what's being seen on the diffraction grating there. And Alan Cale is also involved in this, and Paul Hatherley, who was with us at that time, I think he's at the University of Derby now. And this was 2009. These things are going on, and we integrated them and developed them and took them further in the OpenSTEM Labs concept. I think the last thing I want to do, perhaps I've just got one other thing to show, is I just say this is a team. This is a huge team of people, and this was the team as assembled in 2018. Other people have come and other people have gone since then, but a massive effort of a large number of people, all working to a common cause. Well, I said we'd just go somewhere else because Ulrich's with us. I couldn't resist putting this on. This is his telescope.org website. And we looked at it a little bit earlier, and the sun was just going down, and we could see that there were two telescope domes in the middle of here. We can't quite see that from that image. I'm just wondering if I've got that on record. So did I capture it? No, I rather hoped it would stay. You'll see in a minute when we cut to the other shot that Ulrich has got the camera, the domes behind. And in fact, maybe if I go to just that view, do I get, where should I go, Ulrich? Main page, I suppose. Try that. There we are. There we are. There's one of his domes opened up on Tenerife. That's Mount Tidy. That's a quiet volcano. I think we've got 100 years since it last erupted, and we're just hoping while we've got this kit here that it doesn't erupt again for the time being. It's quite expensive stuff. Put there under the auspices of the OpenSTEM Labs, which is what I've been talking about. Sally, team, I'm going to stop at this stage and I will unshare.
Thank you very much, Nick. That was a fantastic lecture, very interesting and very good to hear your perspectives on the history of both X-rays and the OpenSTEM Labs, and a good showcase of what we're doing here. We're getting lots of questions coming in and comments as well, so we're just going to prioritize those. The first thing I want to say is ask the audience, please, if you do have time, can you please fill out the demographic survey? It really does help us. I know I keep hounding on about it, but it's really important to us, and it really helps us to show what we're doing here is valuable. So I myself had a comment, and I think I'll start off with that because it's not often that I am able to comment on your work since it's normally so thorough. So I just wanted to comment that, of course, in many European languages and Japanese and Hebrew, they are referred to as Röntgen rays instead of X-rays. Röntgen himself was very opposed to the idea of calling them Röntgen rays, and that's why they're X-rays in English, but other languages just went ahead with it. We have a comment from a certain Liz. I can leave it to people on the call to guess which Liz it might be. She says, thanks for some fascinating history, but I would not want members of the audience to go away thinking that the Braggs were the first people to do medical imaging with X-rays. It was, in fact, Röntgen, who was a very careful experimentalist, and when he spotted the X-rays, decided to do some experiments. He established first that they traveled in straight lines, that they penetrated some substances more than others, and then that they would expose a photographic plate. And he then went on to take some images of his hunting rifle, identifying some faults in the barrel. He then got his wife to put her hand on the photographic plate and produce the first medical image, which was then published in January 1896. Following that publication, a lot of other people had a go, including the Braggs. So
can I just add to that?
Of course.
That is entirely right. In fact, the US military had also used it to find one or two bullets that had gone under the skin. So also in 1896, it caught on so quickly. It is astounding the speed with which it caught on. It must have been truly amazing to suddenly be able to see inside. But as we have noted, a little bit dangerous.
Great. So now we move on to some questions. So first of all, we have a question from Rodney, and he asks, someone who signed off as C. I have found the lecture truly fascinating. I think it's great how we've developed doing live experimentation at a distance. But she would like to ask how the X-rays are used in planetary physics to infer things about targets, if indeed they are.
Yes, they are. For if you're doing planetary stuff and you land on the surface, what you can do with an X-ray spectrometer is to use that kind of Bragg, the Lowy method, actually probably the Lowy method, to look at diffraction, and you can from that determine the crystal structures. And since we've got a lot of crystals here too, by comparison, you can work out what the minerals are just by straight comparison. And with the fluorescence method, you shine energetic X-rays at something, and characteristic X-rays of other things at lower energy will come out. So if you shine what I was showing is X-rays down onto the surface of say, copper. If I put a copper coin in there, you get fluorescence from copper, and so you'll be able to detect materials in that way. And then, of course, there's X-ray astronomy, but that, I think this is mentioned specifically Planetary. Is Monica still in the room? Because she would be able to say more than that, I'm sure.
She's disappeared.
She's disappeared. She's okay.
But yes, I know certainly my research group is involved at the Open University in instruments that do X-ray detection and fluorescence from other planets to work out what they're made of. So a follow-on question, and this is from Rodney. He's asking, what next? What about open space labs? Can we put CubeSats in Earth orbit with instruments that students can then configure and receive data from?
Well, we've got the first part. We've got to. I haven't checked to see whether it's still there. The thing about CubeSats is that they will come down eventually or burn up. But we did invest in a CubeSat with a camera from your group, Ben, on board, and we have communicated with it. We haven't built it into the curriculum, unfortunately, yet. Too many ideas, not enough people. Yeah, so and more of it. And don't forget, we've got a Mars yard as well, where we can simulate the Mars environment and run rovers around, which we do at the moment.
Fantastic, thank you. We have a question from David. He's asking, can the OpenSTEM Labs ever match the hands-on experience of the old experimental kits? They're fantastic. He's used the SEM and the scopes and other things on S818. That's our Space Masters course. And he's really enjoyed it, but it's not quite as exciting as the massive experimental kits for S101 that arrived on his doorstep almost exactly 33 years ago. Any comments on that?
I'll give a practitioner's comment on it. I mean, I agree with you. I'm a twiddler, a player, a doer, and so on. Pedagogically, we have to work. I mean, we're here to make sure that we're trying to share and transfer knowledge and so on. Those home experiment kits that we sent out in the early days were returnable. Had quite a large number come back unopened. So, you can give people how do you get them in there? I'm hoping that the OpenSTEM Labs approach is another way in which we might encourage people to open the box, so to speak. But it is a challenge. And like I said, it was to do with also the range of stuff that you were putting in there. Nowadays, you'd probably find there are regulations about it. Kitchen sink stuff where you just got stuff at home, you can do that, and you can go a certain way. But in the end, laboratory work with expensive kit gives you richer insights in some of the things. I mean, somebody's right. You can measure the diameter of the moon or something like that, the distance to the moon, with just kitchen drawer stuff. But there are certain things that we can do, like X-ray experiments, that you can't. I mean, how would you do that at home? I'm not going to send X-ray tubes to students.
Great, thank you. I guess I have a question, and maybe this is a bit too political for tonight, but I'll ask it anyway, and you can sidestep it if you want. Clearly, a lot of other universities are thinking of replicating the success of our OpenSTEM labs due to the current condition where they are having to mail out experiments to their students to perform. I just wonder if you can comment on, what we are doing to keep ahead of the curve in terms of that.
Well, I think I'd like to suggest that we're investing in order to keep ahead. There are some great things that will be done in that way. In fact, we're also sending some kit out later this year to our engineering students. We're going to be sending them shaker tables so that they can build a structure and shake it as if it was in an earthquake. Some nice things that you can do like that. But I think we've got places to go. We've played a little bit with virtual reality. We might do a little bit more of that. I'd like to get tactile. I'd like to be able to feel some of the textures and surfaces. I'd like to get that sense of resistance when I'm moving the knob. So there's more that we can do there. So taking people collaboratively to places that they couldn't otherwise reach. There's quite a lot that we're looking at and go to. Somebody was teasing me the other day and saying, well, what about smells? I mean, the chemistry laboratory, how do you get that feeling? For years now, you've been able to get a little plug-in to your iPhone if you want that will use a few selected aromas and send them out, and you're trying to give you the impression that something smelly is happening. I don't know. Can I transfer the question a little bit and just ask Alan Kalis if he wants to add anything there? He's added an experiment recently, which is way ahead of what the others have been doing.
Right. Thank you very much, Nick. Well, yes, we're very, very proud to have the use of the Open Science Labs across the whole of our physical sciences curriculum, from level 1 modules where they'd be doing the Bragg experiment, to my own remote experiments in physics and space where we do the Compton and use the telescopes that are sat there behind Ulrich. I'm not sure you're actually out there in Tenerife at the moment, but we can take our students out there and have them using equipment that is on a par with professional grade observatory telescopes. And then at postgraduate level, we have the S818 Space Science Masters, where we use the telescopes again, and we do actually do a case study on CubeSats, although we don't actually fire them up into space at the moment. We could do in the future. And we have the Mars rover activity. So all of these things, as Nick was describing, give the students opportunities to do exciting science using equipment that they couldn't get their hands on even in a sort of traditional science lab, as it were. And they also help the students, as well as the reason for doing an experiment, of course, is driven by the science. We investigate these amazing phenomena, these quantum mechanical phenomena. Our students can investigate and prove to themselves that photons carry momentum. But in doing so, and in an interesting way, perhaps more so with the remote experiments, they also develop these skills of analyzing, understanding the experimental design of a piece of equipment, how to interpret an experiment. Nick mentioned the process of calibrating the equipment. And so it's about skills development as well as learning the science. And that's one of the real strengths of the Open Science Laboratory. It allows the students to do that, working in a collaborative way with their tutors and with the other students. So all of these skills are really, really relevant, because a lot of science is done that way these days. As a professional astronomer, I might request time on a telescope. I'm less likely to actually physically travel there and peer through an eyepiece these days. If, as you know, we're looking forward to the landing on February the 18th of the Perseverance rover, and if you're operating a space telescope, those are up-to-date research science experiments that by definition are operated remotely. So the skills that we have through the Open Science Lab, it is hands-on science, it's bang up-to-date science that's done in the way that science is progressing, operated remotely, developing precisely those skills that the students will then go on and work in the space sector or wherever their career takes them. So very, very proud to be a part of it.
Super, thank you so much, Alan, for that. I think I'm going to finish with one final question, and this is for anyone to chip in if they feel like they've got an answer that they're happy with. I guess if budget wasn't a concern, is there a specific experiment that you would like to see on OpenSTEM Labs that we don't currently offer, but you'd like to see at some point in the future? Start with Nick.
Please, I'd like to pass it, because this will help me understand what the ambitions of Ulrich are for the Open Science Observatories. What do you want, Ulrich? I think I know the answer, but tell me what you want.
Large. I want large. So large is better as far as astronomers are concerned. So a really large telescope to add to the existing ones would certainly help. But more seriously, either one at a different location on the globe, so that we have true real-time access to telescopes 24 hours a day, not just during nighttime in Tenerife, or to add spectroscopic capability to the telescopes, which currently are only doing photometry, only in quotation marks. So, that would be my immediate wish list. But if the pot is unlimited, I can go really large, and let's put a telescope on the moon. Thank you.
I should probably say that the pot isn't large. I'm the voice of realism, as is Nick. I've seen Monica, I've seen you laughing, and I'm about to come to you in a minute. I'm not going to give a specific answer, but I'm going to throw the gauntlet down a little bit to my colleagues. One of the things that actually the Open Science Observatories have done is enabled the telescopes that we are using in our teaching also to be used for research. Hold that idea, and also bear in mind that across the sector it's becoming very much more common, to have the interface between people researching and people learning much closer. And I'm not looking for answers, but I'm just thinking to colleagues in the School of Physical Sciences and across the Open University, what research are we doing? That if we could have something of that we were able to engage all of our students, wherever they are in the world, to actually participate in that. That is the sort of thing that I would be interested in doing. I don't know, Monica, if what you were going to say comes with that at all, but I'll hand over to you then back to Josie, I think, who's going to finish up this evening.
Well, this is answering Ben's question about what we would like to see in the open labs, and it follows on from Ulrich. For telescopes, bigger is best. Bigger is better. For me, as a microscopist, small is good. But spectroscopy is where it's at. All wavelengths, not just electromagnetic spectrum, but Raman spectroscopy, so the vibrational stuff. I think we could get some really interesting experiments marrying what's happening with telescopes with what we can look at on Earth in the labs. And sort of doing some really good effective planetary science, marrying those two things, and I think that would be a really great thing to do.
It's interesting we come back to seeing at a distance.
Well, seeing I'm talking about Raman.
Yes, I know.
And also well, a lot of infrared actually. So yeah. I suppose that is seeing.
Yeah.
But it's not just imagery. All right. So seeing isn't image.
No.
You've got to have something with it as well.
Yeah.
And I was here all the time. I just want to say, Nick, I was here all the time. I was just on Stadium, not on Teams. Because I've been. Cheers.
Josie.
Well, I hope everybody's enjoyed tonight as much as I did. Thank you so much, Nick, and colleagues from the school for chipping in at the end there for a very inspiring evening. I'm delighted to be able to close out the evening and offer a few thanks on behalf of the Open University. So obviously, first and foremost, a chance to thank the Institute of Physics for recognising Nick's work with this prestigious prize, and by extension recognising the innovative work by many colleagues at the OU, as Sally explained in her introduction. I really enjoyed hearing a bit more about the history of the teams. And I'd also like to thank the Institute of Physics Southeastern branch, who have been supporting this series of lectures. Lots of appreciative thanks to Ben for hosting, Alice Dunford, Rosa Miller for their work in organising the event, and James Smith and Jeff Austin, who with Ben have set up the OpenSTEM Labs demonstration for all of us to go and have a play with. I'm looking forward to exploring that a bit more. And of course, the reason we've all been able to see everything this evening is thanks to Keith Hamilton, who did the audiovisual support for this evening's event. So thanks to Keith too. I think tonight's session for me has really illustrated the OU's spirit of innovation and our embracing of a diversity of methods to reach students everywhere. So I'd especially like to thank all of those colleagues who have contributed and continue to contribute to the authentic, innovative teaching of practical science at the Open University, something of which I think all of us are very proud. And last but by no means least, thank you all for attending this evening, for some fantastic and interesting questions. I hope you have a lovely rest of the evening, everyone. And Nick, congratulations again. Thanks all.